Let us now discuss another converter, very popular converter, one of the most popular converters that you will find in most power electronic equipment, that is the flyback converter. It is a buck boost derived converter. The forward converter was a buck derived converter. The flyback converter is the buck boost derived converter. And let us see how the isolated buck boost derived converter looks like. So let us begin by drawing the circuit of the buck boost converter, and let us derive the isolation from that. So we have the source, you have the switch, control switch, inductor, uncontrolled switch, diode there, the capacitance and the load. So this is the buck boost converter which we know and which we have discussed, and we know its operation function. Let us now name the parts. You have Vi measured in this fashion, R0, V0, L, C, Q, control switch, D, diode. Observe that when the switch Q is on, the inductor current flows in this direction. When the switch Q is off, the inductor current will flow in this fashion, charging up the capacitor in reverse. So this is IC, I0. Now I will make one modification just like we did in the forward converter. This control switch is on the rail side. This switch has to be driven to saturation on and off by controlling the voltage across its base and emitter. The emitter is lifted up, floating. It is much better to have the switch ground based, and the drive ground based drive is much easier to make. So without loss of generality, we can move this switch from the top rail to the return rail, maintaining the flow of the current path in the same manner. So we can place that Q here. So you see the current flow is in this path when the switch is on, and the return path for the current is in this path, in this direction. So we are still maintaining the same direction of the current flow, and we can remove that switch. So we have shifted the control switch to the ground rail. We can mark the ground, this as the circuit ground, and we can label the positive of the input source Vi like this. And in order not to clutter up the circuit, you can remove that. We can do next step of the modification, make this portion vertical. Let me draw the control switch vertical, ground, and that becomes Q. Erase this portion, and you can shorten this in this fashion, and so this becomes the non-isolated buck boost converter. So now let us introduce the isolation. This portion of the circuit, we will push it out and introduce isolation here. Observe that this is an inductor, and we are winding one more winding on the inductor so that it provides isolation. But the behavior of this magnetic will still be inductor energy storage. So let us put in one more coil there. Let me make some space arrangements. Put in the core and put in the secondary coil, and then connect it in this fashion. This is still behaving as an inductor L. The behavior is like an inductor, not like a transformer. Let me put the dot polarity here, in this dot polarity. The operation is as before. So we have the Q here. When the Q is on during DTS time, you will have current flow like this, and the voltage across this is Vi. The voltage across this is Vi here, N times Vi, and reverse biases the diode, because here it is plus minus reverse. So this, the V0 and the secondary voltage will reverse bias the diode. And then when the switch is off, there is a reversal of polarity. The non-dot end becomes positive, non-dot end becomes positive, and that will drive freewheel through this diode and charge up the capacitor. So the buck boost operation is still maintained. We can do some more modification in the circuit to make it a bit more attractive. So what we can do is first remove these markings, this diode and the dot polarity. Let us reverse the diode. If you reverse the diode, I should reverse the dot polarity, so that when the non-dot end is positive, the diode should be on. And if you reverse the diode, the capacitor will get charged in this direction, plus and minus, and we will have, as measured in this fashion, a positive voltage. So just to make it more pleasing in that fashion, we have reversed the position of the diodes and the dot polarities without loss of generality. The operation still remains the same. So this is IC and this is I naught. You have IQ here. This is the primary voltage Vp across the inductor, measured in this fashion, and the secondary voltage Vs, this is D, and this is ID. Okay, we'll push it out, and then let us say that there is a turns ratio between the primary to the secondary as 1:n. Now, in order to understand this circuit, now this is the complete isolated buck boost converter, also called as the flyback converter, very popularly called as the flyback converter. And look at the simplicity of it. You have one switch, you have one magnetic core operating like an inductor, and you have one diode and one capacitor. Simplest, least number of component count, and that is why it is so popular. Now we know how the buck boost converter operates. This is entirely similar to the operation of the buck boost converter. Notwithstanding that, we should draw the waveforms and try to understand its operation. But let us relook at the buck boost converter. So this is the buck boost converter that we had discussed some time before, and the waveforms here. So VL, this is the voltage across the inductor. Remember this. The current through the inductor, IL. Now the current through the inductor will be split into two parts: current through the primary of the inductor and current through the secondary of the inductor, which I will explain, and the currents through the switches here. So let us copy this portion of the waveforms and paste it alongside the flyback converter and try to understand the operation of the flyback converter with these waveforms and try to modify these waveforms to fit the variables in the flyback converter. So let us now paste the waveform here, move it around, make some space, and this is the waveform that we will try to map here. So VL here will be Vp, primary of the inductor of the flyback converter will be the VL waveform. DTS is the period of time when Q is on. 1 minus DTS is the period of time when Q is off. Again DTS when Q is on, 1 minus DTS when Q is off. IL is the inductor current. We will split that into the primary inductor current and the secondary inductor current. This portion flows through the primary, and this portion, the falling slope portion, will flow through the secondary. And let us rename some of these variables to map into this circuit. VL here, the voltage across the inductor, is indicated as Vp here, voltage across the primary inductor, and Vs, voltage across the secondary inductor. So let us replace this VL with Vp, voltage across the primary inductor. Now the voltage across the primary inductor during the time dTs, when the transistor Q is on, the entire Vi comes across the primary inductor. So let us indicate that with the plus, dot end is plus, non-dot end is minus. On the secondary side, you have the dot end plus, non-dot end minus. Observe that the voltage across Vs is N times Vi, and that plus V0 is coming across this diode and reverse biasing it and switching it off. So what is that voltage which is coming across the diode, reverse biasing it? N times Vi plus V0 comes across that, and this will reverse bias and switch it off. Therefore, during the time when Q is on, during DTS time, only the primary current is flowing, the secondary is off. Of course, the capacitance is discharging to the load. Observe also that during DTS, the current that is flowing through the primary IQ is only for the part DTS, and during 1 minus DTS there is no current flowing through that. The only link between the primary and the secondary side of the inductor is the flux. So let us indicate that flux here, and IL we will replace it with flux. So this is the flux waveform, but we have to change these values. So let us say here flux is phi average, this is the average phi, and the slope is not Vi by L. Vi by L is for the current waveform, and here it is Vi by. Now if I say this is NP and the secondary is Ns number of turns, so it is Vi by Np, the slope, the rate at which flux changes. Now what is the waveform of the current that is flowing through the primary, or the current that is flowing through Q? IQ. IQ is nothing but the current that was flowing through throw 1 to pole current, that is IT1P. So IT1P becomes IQ. So see that during the DTS period of time, IQ, there is a current which is rising linearly like this, and the slope there is Vi divided by L, and that is the slope of this. So observe that IQ, you will have a finite current only when Q is on, and during the period 1 minus DTS, Q is off and there is no IQ. IQ current is 0. Now what is the current through the diode D, ID? Let us change this T to P. It is from throw 2 to P of the buck boost topology. That becomes ID. And as you can see from this operation, when Q is on, dot is plus, diode is reverse biased, diode is off, there cannot be any ID current. However, the capacitance is charging into the load, so you have a negative I0 flowing through at that time, discharging into the load. Now let us take the time period 1 minus DTS. During 1 minus DTS, Q is off. So the Q is switched off, IQ will become 0. And what will happen to the polarities of the primary and the secondary of this inductor? So you will see that the non-dot end will become plus, dot end will become minus, non-dot end is plus, dot end is minus, and you will see that Vs, the secondary voltage, will rise up to that level just greater than V0, so that diode D is forward biased and diode D will conduct and charge up the output capacitance. So Vs will be V0 because the diode is conducting, V0 will come across Vs. And what will be Vp? Vp will be V0 by N because there is a 1:N turns ratio. So Vp will be V0 by N. And how does it reflect onto the waveforms? You will see that Vp waveform during 1 minus dTs will go negative, but the amplitude of that voltage across Vp will be V naught by N. So let us mark that V naught by N, and in the flux waveform it will be V naught by Ns, because V naught is coming directly across Ns. V naught by Ns will be the downward slope of the flux waveform, downward rate. IQ is 0, Q is off, IQ is 0 at that time, and ID is the current through the diode. Now the current through the diode, observe the flux minus V naught by Ns, because the non-dot end is positive, it is going to be a downswing current flow and also the flux. So the current will have a rate of minus V naught by N square L. L is on the primary side, on the secondary side will be N square L, and that will be the slope of the current there. The average of ID will be I naught, like before in the case of the buck boost converter. The current wave shape of the capacitance will remain unchanged, and it will be of the same shape and amplitude, because the output portion we have not changed anything. Now let us try to find the input output voltage relationship. So input output relationship, first the voltage, we apply volt second balance for the voltage waveform across the inductor. You can choose either primary or secondary. So let us say we take the primary voltage across the inductor. So during dTs we have Vi, during 1 minus dTs we have V naught by N. So use that. So you have Vi into dTs plus V naught by N into 1 minus dTs should be equal to 0, volt second balance. You can remove this variable, and then on simplification, and if we take only the magnitude of V naught, because you don't need to worry about the sign, because you can take anything as ground because it's isolated, it will be N times Vi d by 1 minus d. So this becomes the input output voltage relationship. Note that the output voltage is having N as one degree of freedom and D as the other. So D is a variable. It can continuously vary on the fly during operation. So you can use that as a control input. N is again a variable which you can change only once at design time. So this can be a designer variable. So by design choice you can fix the value of N. So you have more flexibility in choosing the output. Now likewise for the current also, you can get the input output current relationship. You can use the power balance relation. Vi into Pi is equal to P naught, Vi I average is equal to V naught I naught, and V naught you can replace using the input output voltage relationship. So we have Vi into II average equals N Vi d by 1 minus d into I naught. So if you cancel out Vi, you will have II is equal to N I naught d by 1 minus d. So this would be the input output current relationship. You see that IQ is having an average current, which is the II average, and that value will boil down to N I naught d by 1 minus d. You know d, you know N, and you know I naught. You can evaluate that. When the transistor Q is off, when we saw that when the diode D was off, the peak inverse voltage that it needs to support was N times Vi plus V naught. And for the case of the transistor, when it is off, it has to support a voltage of Vi So you have supply voltage Vi coming across that, plus also the reflected voltage from the secondary at the time when this is off. Diode is on, there is V0 coming across this one, and on the primary side it is V0 by N with plus minus in this fashion, plus minus this one, plus this Vi. So you have V0 by N together coming across the collector emitter of Q. So you will have to rate the VCO rating of Q to be greater than Vi plus V0 by N. So in this fashion we have this flyback converter, which is this is the functional schematic of that, and you can use that, and it's very, very popular. And you can also have multiple outputs. You can have multiple secondary windings across the wound across the inductor, and you can take out isolated multiple outputs from this flyback type converter.